Hi, it's Mr. Hannah here. Welcome to this little series. It's about math methods basic knowledge. So basically this is stuff that we were hoping you would know before coming into maths methods from years 7 to 10. And there's four things that we're going to cover in this video, and then there'll be a couple of other videos afterwards. So this one's all about things you can do. So it's sort of about manipulating expressions, or just manipulating algebra, I guess. Okay, so there are four things you can do. Firstly, you are able to add 0. That doesn't change anything. Second thing you can do, you can multiply by 1. If you multiply by 1, you're just going to get the same result, so you haven't changed anything. So you're allowed to do it. Number 3, you're allowed to do any operation as long as you follow it by its inverse. Do any operation, then its inverse. And number 4, this number 4 is if you actually have an equation, not an expression. So this one's for equations. For equations, you can do anything. Do anything as long as you do it to both sides. So you can do anything to both sides. Now this video is going to be explaining those four things and giving you some examples of how they sort of work. So, number 1, adding 0. To add 0. Okay, so adding 0 doesn't change anything. That seems fairly obvious. Like if you have 5 plus 0 is 5. So when you add 0, you get whatever you started with. So if you have x plus 0, then you get x. Now, this seems fairly useless in the way I have written it here, but think about writing 0 in a clever way. So write 0 in a clever way. Well, what do I mean by that? 0 in a clever way, it could be something like plus 9 minus 9. Okay, because plus 9 minus 9 does equal 0. So if you've got x just by itself, you can add 0 by adding plus 9, take away 9. That also equals the first thing we started with. So we haven't changed x in any way, so we're allowed to do that. Now, one of the places where we actually do this is in completing the square. So for example, completing the square, we've got, say, x squared plus 4x minus 1, for example. So hopefully you remember with completing the square, you look at your middle term and you halve it. So you go a half of 4 is 2. So what you would like is this perfect square, x minus 2 squared. But if you did have x minus 2 squared, you would have x plus 2 squared. X squared plus 4x, because first you double it, and then you multiply it, and then you square the 2. So it will be x squared plus 4x plus 4. So that's what you've got here with this perfect square, but of course you can't just go around putting in a plus 4, because you've actually got minus 1 here. So to get a plus 4 there, you can add 0 by doing a plus 4 minus 4. So now, the x plus 2 squared bit is this part, and so then you've still got a minus 5 at the end. And now it's in turning point form, and you could keep going with that if you like, but I just wanted to show you that that is an example of adding 0. So add 0, I'm just going to write example, completing the square. Completing the square. let's corner that off. Alright, so there we go, there's adding 0. Now, our next thing that we had was multiplying by 1. Okay, multiplying by 1. So here, if you start with x and you multiply by 1, you get x. So you've gotten the first thing again, so you've done nothing by multiplying by 1. Or if you've got, say, 7, and you multiply that by 1, you get 7. So once again, you get what you started with. So you're allowed to multiply by 1 at any point because it doesn't really do anything. Now, just like the other one, this seems utterly useless at the moment. But what if we write 1 in a clever way? Okay, if we write 1 in a clever way. So, for example, 1 is the same as 5 on 5. Or it's the same as x on x. Or it's the same as 3x on 3x. Okay, these are all 1. So these are equal to 1. All the same. So when is this useful? Well, you'll know from fractions, it can be quite useful for equivalent fractions. So if you've got, say, I don't know, 5/6, what you're allowed to do is you can multiply that by 1, but instead of just writing your 1 like that, you can write it like 5 on 6, you could write it as 2 on 2, and that way you get 5 times 2 is 10, 6 times 2 is 12. So 5 on 6 is the same fraction as 10 on 12. And there's another way, another thing with surds that you can do, which is a multiplying by 1 thing. So there's multiplying by 1. A couple of examples for you. Okay. Number 3. You can do anything, or do anything, that's any operation is what I mean there. Any operation followed by its inverse. Okay, so for example, I could start with 5, and if I multiplied that by 3, but then divided it by 3, I get out 5 again. Because times 3 and divide by 3 are inverses. Okay, so another example could be that I have x, and I could divide that by 6, but then also multiply it by 6. That gives me x back. Okay, so the reason these cancel out is because they are inverses. Okay, you could have more complicated looking examples. Suppose I have x again. I could take the sine of x, but then I have to follow that by doing the inverse. And the inverse of sine is, well, it's called just the inverse of sine. So there you go, the inverse of sine of x is x. Okay, it's the same thing that we started with all along. And that's because sine and inverse of sine are inverses. So that is something you're allowed to do there. Now, when is this useful? Well, it's very useful for doing difference of perfect squares, or also known as DOPS. So you remember hopefully that difference of perfect squares, if you've got x squared minus a squared, that is x minus a times x plus a. Okay, but what if we have x squared minus 10? Well, the x squared bit's there, but 10 is not a square number. But luckily we know that 10 is equal to, well, we can do the square root of 10 followed by squared, because the square root and squared are inverses, so they cancel each other out. So that means we can write this as x squared minus the square root of 10 squared. So now our a is the square root of 10, and so we can simplify that to x minus the square root of 10 times x plus the square root of 10. Okay, so there's an example of doing any operation followed by its inverse, and you can do that at any time. Okay, lucky number 4. Things you can do. So you can do any operation to both sides of an equation. Okay, so the key is, the key here is doing it to both sides of the equation. So here's a very, very simple equation, x equals 2. Now I can do any operation, so I'm going to choose to do times 6. So if I do times 6 to both sides, my new equation will be 6x equals 12. Then I might choose to do a divided by 5 to both sides. My new equation is 6x divided by 5 equals 12 divided by 5. Now I might choose to do everything to the power of 3. So I'm doing to the power of 3 to both sides. I now have 6x divided by 5, power of 3 equals 12 divided by 5 to the power of 3. And so on and so on. I can keep doing things. I could do sine to both sides if I wanted to. Sine to both sides, and it would still be the same. Okay, so anything to both sides of an equation. And this is in fact how we solve equations. So, e.g. just solving equations. This is exactly what we do just to solve any old equation. So let's make one up. We could have 7x plus, plus 4 divided by 3 equals 1. Okay, so what we're trying to do to solve this equation is get x by itself, and we're going to do it by doing a series of things to both sides of the equation. So first we're going to try and get rid of the 3, so we'll do a times 3 to both sides. Now because we've got inverses here, the divide by 3 and a times 3, they cancel out. So we're left with 7x plus 4 equals 3. Because 1 times 3 is 3. Now the next thing we're going to do is get rid of the plus 4. So we'll do an inverse, minus 4 to both sides. These bits cancel out, and we're left with 7x equals minus 1. Now we've got a times 7 here, so we're going to do a divide by 7 to both sides. These are inverses, they cancel. We've got x equals minus 1/7. So there we go. Number 4, do any operation to both sides of an equation. So there we have it. I hope you've learned a couple of useful things, or at least refreshed your memory, or made you understand what some of the things you were doing in years 7 to 10 were really all about. Alright, hope to see you next time.